Jacqueline, what is your understanding of experimental unit? Jacqueline? Is Jacqueline there? Who can give us, define for us an experimental unit?
Yes, Doctor.
Are you guys hearing me?
Yes, I can give it a try.
Yes.
I think
Yes, please.
an experimental design unit can be an entity within a research, like a specific interest that is being studied in a research.
An experimental unit is part of a unit where the treatment is applied.
Okay, where the treatment is applied. So there is Brian O. Who is Brian? Who is Brian? People not signing and then they disappear.
Brian, we are here. We are here.
Brian, you have, yeah, Brian, you have a St. Peter's statue. You have an artwork from St. Peter's College, Tororo. Can you tell me what an experimental unit is? Is Brian there? Okay, Teddy? Hey, this is supposed to be the same as class. People are supposed to make contribution. Jonathan Mugero?
Yes, doctor.
Yes, what is an experimental design?
Okay. Design for individual components. Yeah.
Okay. Okay. So an experimental unit is defined as the smallest unit of the experimental material to which the treatment is applied. So here, for example, each rat can be an experimental unit. When we're dealing with completely randomized design, the assumption here is that each of the experimental units that we are dealing with are homogeneous in that they are very similar. So as you can see from the rats here, we can see all the rats look very, very similar. Okay. So here, what implies then that since the experimental units are very similar, what we need to do in this case is that we need to get a way of assigning treatment to each of the experimental unit so that each experimental unit has an equal chance of receiving any of the treatment that we have here. So for example, any of the rats, let me try to get, so any of the rat can receive any of the treatment. Let me go back to the previous slide. Now I told you to download and install ARA and ARA software on your computer? How many people have installed R and R Studio on your computers?
Yeah, mine is installed, doctor.
Yes. So can you, each one, you put type 1 if you have installed R, type 1 in the chat room. Those who have installed type 1. Okay. Mariam. Okay. So is there anybody who has not installed? Okay. So we what we are going to do is we are going to use ARA to help us to do what we call the randomization process. So the randomization process, based on the definition we had the other time, is simply the process of assigning treatments to the different experimental units. And as I showed you earlier on, so if each of these rats is an experimental unit, then we need to decide which rat number one, what kind of treatment rat number one will get, what kind of treatment rat number two will get, and so on and so forth. That process can be done using ARA, and you need this simple command here, and then at the end of the day you should be able to do that. Now you have the presentation with you. I'm going to maybe spend about 30 minutes trying to get each one of us to open ARA and ARA Studio, and then we look at a few of those things here. Okay. So here, all experimental units are assumed to be similar with respect to the characteristic like to affect the response. So this is the type of experimental design that is used very frequently in the laboratory on a screenhouse or in screenhouse experiment. In most cases, like in agriculture, using it in the field is very rare. But for most of you who are in food science, this is the type of experimental design you like to use in the lab. Now the problem with this is that since this experiments this design assumes that all the experimental units are uniform, I need to let me try it. Just hold on a bit. Okay. So if you look at these rats here, you can see that the rats are similar, and hitting you have the similar color. So once we give the treatment to each of the rats, we are going to observe that there is going to be some variation in the measurement that is done. So here, for example, we can see that rat number one, we got reaction time of 10 seconds, rat number two, 9.5 seconds, rat number three, and rat number four. Now, from this is the variation that the other time we defined as our experiment variance. And 0.72, let's say 0.73. So this is the variability that is existing among these rats when we treat the rats with the same treatment. We give them the same treatment. Let's say some kind of a drug and so on. Now, when we come on this side, for example, we can see that we have different dogs. The dogs are treated the same way. Now, the reaction time of the dog, like we say for this one, yes, 50, then 90, then 150, then 500. So from here, we look at the variability that we calculated. This is about 42,000, let's say 600. 42,360. So you can see that the variability among the response of the dog is much higher than the variability among the response of the response time of the rats. Now the difference between these two is partly because the dogs are of different types. And if we are sure this variability will be considered to be an experimental error, but we know for sure that apart from the experimental error, there is also kind of variability that exists between these different dogs. So the types of the dog is very, very different. So in this case, we're saying since randomization is unrestricted, the experimental error include the entire variation among experimental units except those due to treatment. So you can see here that the treatments are the same, so there's no variation between the treatment. The only variation that we observe here is what we call experimental error, plus if there is any variation between the different animals. So like in this case, we have variation between the different types of the dog used in this experiment here. So because when we are doing experiment, it's always not true that the experimental units are homogeneous. So if we look at the animals we have in this case, you can see that these animals are different, and therefore you'd expect them to behave differently. Even so, let's say, for example, you are testing effect of drugs. So let's say we want to test the effect of drugs. Now, what could be the possible challenges we get in using these animals here to compare our experiment? So I want to see. So what could be the challenges that we get here, Daniel? Daniel, I seeing the ants in my mouse. Is Daniel there? Bakabinge? Can you unmute yourself and say something? Yes, Daniel. Are you talking? Is anybody hearing Daniel?
No, doctor, I'm not getting
Not really.
him.
Not really. He has not yet
Eh,
started talking.
so Daniel, what is happening? Joanna? Joanna, can you tell us what could be if, let's say, I'm comparing this big bull here with the one with this particular the cow next to it. Let's say I'm injecting this with the drug A and injecting the other with drug B. What could be the problem with my conclusion when I draw conclusion that one drug performed better than the other? What would be the weakness of the study?
Doctor, can give it a try.
Yes.
I would think there would be variability because the animals are of
Mm-hmm.
different species. of different health ways. They don't have the variation in immunity.
Okay.
Yeah, this one to be seems to be immunocompromised as compared to the bull. So probably that also would cause
Okay.
a little bit of variation. Yes.
Okay. Tom, you raise your hand up.
Yes, doctor, the variability will be there because if you look at the bull, it's healthy enough. So if we inject them with the same drug, we find out that this cow that seems to be malnourished may respond faster due to its low immune system. So the drug
Okay.
may work faster in this animal, nourished cow, than the bull because it's already fat. Yeah, that's my
Okay. Good.
submission on that.
Thank you. Taiba Justus. Taiba. Taiba. Justus. Apollo. Teddy. Please, can you
Yes,
sign in with your name that, yes, Teddy?
I think I agree with what Titus said. One of the cow is of a different breed, and one is malnourished while the other is healthy. So the drug will work differently, and you can't make conclusions
Okay.
on that. Yes, still they will respond
Joseph.
differently.
Kauma. Joseph. Will they respond differently? Yes. Yes, Joseph. I'm waiting. We're waiting for you. Okay. Okay. So in that case, we cannot use completely randomized design. Uh, Completely randomized design assumes that the experimental units are uniform. So in this case, experimental units are not uniform. Therefore, cannot use uh, we cannot use completely randomized design. We can use another design. The other day we defined as grouping of experimental units together such that within the group there is uniformity and between the group there is some differences. So here the experimental units are a material. There is a predictable trend in variability in experimental material. So the best thing to do in this case would be to group your experimental units in. So this one works on the assumption that you know your experimental material quite well. So here, for example, we have different breeds of dogs, so we can use as a block. This can be our block number 1. This can be our block number 2. This can be our block number 3, and this can be our block number 4. So here, then, we can make our comparison within the different blocks. Now, in a lab, okay, let's say if you have those who are doing human nutrition, for example, what would be characteristic that you can use for blocking your experimental units? I need an example. Who is the person using iPhone? I would prefer that you sign in with your real name so that if I'm taking my roll call, I know whom I'm dealing with. Otherwise, I might consider you to have missed lectures, yet you're there. Can my OB Brian now talk? Yes, the iPad person.
Yes, doctor.
Yes.
Pardon?
Give an example of experimental unit that you can block in your experiment.
Um, where is the fine? Well, I would, I would, I would use what do I call it? I would, I would use for example, use best.
If you're using women, a human being as your experiment unit, then you can group them using age. So you
Yeah.
can have different age group. Maybe you have
Mm.
the youth, maybe you have the middle age, maybe you have the old. Okay, that is
Yes.
good. Fred Mugarura.
Yes, doctor.
Yes, so give us an example.
I think then me I would change and block maybe secrets according to their sex.
There.
According to sex of the
What
maybe
experimental unit did you talk about?
in this case I would use the rats.
The rats. Okay.
So I'll compare the male rats, the effect in male rats and female rats in response to whatever they have
Okay.
been
What about?
exposed.
Will there be differences between the different? I mean, if you look at within the male rats, do you expect them to be all uniform, or they may also be different?
Most likely they will be different. Now,
Mm,
bringing in the age factor and the size as well.
okay.
Yes.
Yeah. So it's possible to have a combination of blocking factors. So you can probably use male and female. You can use maybe the male. You can divide into group different, four different young male, old male. This can be your experimental unit. So here we assume that you know your experimental material well. Let me get another one. Dennis Kabalaga, give us an example before we proceed to the next.
Yes, doctor, I have just plugged in. I'm not ready.
You're not, why are you not ready?
Doctor, I have just joined.
Why have you just joined now? We knew what time the lecture was supposed to begin. I'm sorry, maybe I'm interfering with your Valentine, but
Not really, doctor.
When I was thinking about this, I never thought about that. I apologize. Providence, you give us an example before we proceed. Yes, Providence. Urubai.
Yes, good morning, doctor.
Yes. Yes. Give us an. You are there. You
I'm
also.
sorry.
I
Yeah,
also interfered with your Valentine.
understand.
Okay. So the whole idea is, for example, let's say we look at these different colors to indicate differences in the experimental material. So you can see that block one will consist of unit that are a bit lighter, and then block six will be consist of an unit that is a bit darker. So in this case, block one could be a room that is well lit, and then block six could be a dark room, for example. Or block one could be uh, the experiment you run on day one, and block two could be experiment you run on day number two. Block three could be day number three, and so on and so forth. So you need to see what would be the best case for you. So this is also what we can achieve. We can do the randomization process, because at the end of the day, if now I have my block one with one, two, three, four, five, six different experimental unit, then I need to assign I need to assign my randomization process in within each block separately. I do randomization in block number one, I do randomization in block number two, block number three, block number four, block number five, and block number six. Okay, and this is why I can use this process at some point. So here I can have my block. So I have my treatment A, B, C, D, E, and F, and I want to assign this treatment here to block one, block two, block three, I have to block number six. We are going to come back to this at some point in time. So you can see in this case that my block one now has my six treatment A, B, C, D, E, and F. So here we're saying that treatments are randomized within each block separately. So once you've done your randomization in block one, then you proceed and do your randomization in block number two, in block number three, number four, number five, and number six. Okay. Now, when we come to each block, because we say the block is complete, by complete here we mean that all the treatments occur within the block. So here you have in block one, all the treatments are in block one. You go to block two, block three, block four, and so on. Now, each block serves as a replicate. So in this case, if I'm doing, it will be replicated 5 times. Uh, Let me see. I need to ask somebody. Uh, Ayo, Ayo, what is a replicate?
Replicate means
Is
you
it only
apply
3 times?
that.
What about 2 times? Would that not be a replicate?
Yeah, it's the same.
But 2 and 3 are not the same.
Yeah, it is three. It is three.
Yes.
Two
So applying
duplicate.
treatment more than once, not necessarily as to not necessarily 3 times. Okay. Either.
Okay.
What is a replicate?
A replicate refers to the number of times that a
Yes.
treatment is applied.
Okay.
Hello, doctor.
Yes.
I think a replicate is a repetition of an experiment when it is treated under similar conditions, like when that experiment being
Okay.
repeated is under similar.
Okay. Uh,
May I answer, doctor?
okay. So let's this. Yes, please.
Yes, it is a repetition of a treatment under identical conditions. Repetition of a
So
treatment under identical conditions in an experiment.
okay. So what you're saying here is that if we have treatment A, so treatment A should occur more than once in an experiment. So if treatment A occurs in block 1, occurs in block 2, block 3, block 4, block 5, block 6, then we have, in this case, we have 6 replication because each treatment has to occur in each and every block that you have. Okay? Is that okay, Sammy?
Yes, doctor, that's
Sammy,
okay. Yeah, that's true.
Doctor,
you don't want to add something little?
I can add because
Can you?
I'm saying like in block 1, block 2, like according to the strips, like under block 1, C should not be in the same line in the given block 2, 3, 4 up to 6. Should be in separate, but still
Okay.
appearing on the same block.
Okay. So within a block, we need at least C should be in each and every block. How where C falls within the block is determined by the replication itself. Okay. So this is one way of generating randomized complete randomization in randomized complete block design. I'm going to show you how this is done at some point. And then the other design is what we call a Latin square design. So with a Latin square design, we are controlling variation in 2 different directions. So we have variation in 2 different directions. So with randomized complete block design, you can see that the variation moves from top going down. So as you see, there's a light, the color gets lighter as we go down. Now, in Latin square design, we are calculating variation in 2 different directions. So, for example, for this is more in the field when you go to plant your crops in the field. You might notice that as you move down the field, there is differences in the slope. Let's say maybe this is the lower part of the slope, and this is the upper part of the slope. So here I know that the blue one are all the plots of land that are down the valley, and then this gray one here are the one that are above the valley. So in here you can see that as you move from this point going down, looking at this vertical arrow, you can see that there is variation in the gradients or in the slope of the land. While for the same experiment, there is also variation as you move from this point B, at the corner here, you're moving, there's what we call fertility gradient. So you need then to take both of them into consideration, because if you only block based on the gradients, then you also miss the blocking due to the fertility gradient. So there's the slope gradients, and then there's the fertility gradients. Okay, so this is, I tried to look at it from two angles. Okay, so you can see from here that you can go to, let's say, for example, you go to the field and you find out that there are trees here. So if there are trees on the upper part, so the shading of the tree is going to move down, like you have moving from this light color here to the darker color. So maybe, well, the trees could be here, down here. So you can see that the plots that are far away from the tree are lighter in the color. The ones that are close to the tree are darker in color. But for the same field also, you can look at fertility, subsoil fertility. So here you have low soil fertility, and then this one goes to the high soil fertility. So the two actually are combined together. And that's why it's what we call a Latin square design, because you're blocking using two different trait or different characteristics of experimental material. Now I want to come back and we have a discussion. Can somebody give us an example of two factors that can be used to block an experiment? Diana Ross Ajiambo.
Yes, doctor.
Yes, you give us what you think would be a good example of two factors that can be used to block the same experiment.
Okay, if we looked at malnutrition in children, for example, I would use age and weight of the children as the
and weight.
Yes.
Okay. Okay, you can use age and weight of the children. So you can first look at you can categorize children based on their weight, and then also categorize them based on their age, because you can have a young child with so you can have a young child with low weight, you can have a young child with a medium weight, you can have a young child with high weight, and then like that. So that could be, yes, that is a good example. Obed, can you give us another example?
Yes, doctor. I can look at two factors, that is, say, moisture in grains and the type of variety in connection to aflatoxins.
Okay, how will that be?
Because as moisture varies, it leads to the growth of molds that will increase the moisture, and there are those varieties of, say, cereals which will vary also in aflatoxins.
But in that case, will you be interested in studying the effect of moisture and the effect of variety?
Yes.
Treatment and a blocking factor.
Treatment.
Will variety be a treatment or a blocking factor?
It will be a blocking factor.
And then what would be the treatment in that case?
Hello, doctor.
Yes.
I think one of the example I can think about is age and gender.
Please go ahead. Let's first try to finish what Obed has started. He's saying that, I mean, do we know the difference between a treatment and a blocking factor?
Yes.
What is a treatment?
A treatment could be a substance or something that you want to test its effect on. For example,
Okay. Yes.
if we are going to test
Go ahead.
the response of human beings on maybe a given food nutrient, for example, proteins, like the source of the proteins would be the treatment. And maybe growth, if you're looking at
Okay.
growth,
And what would be a
if we're looking at growth in relation to age, then age will be the blocking factor.
no? Okay. No, you got the treatment issue. The treatment right.
Yes.
The treatment is whatever we are testing to find the effect. No.
Yes.
So Obed said he's interested in finding the effect of moisture and the effect of variety
Yes.
on aflatoxin. Then is moisture and variety, are they blocking factors or their treatment?
I think variety would be the treatment, and moisture.
No, I think moisture is
Yes.
the treatment.
But you can also have more than one treatment in an experiment. So we can have both variety and moisture as our treatment. What could then be a blocking factor here?
Maybe the size of
The size
of the grains.
okay, the size of the grain could be a blocking factor.
How
Maybe
about
the
the
grain
age
coming from
of
a
the
different
grain?
region. There?
The age of the grains, like the maturity level of
Yes,
the
that could be
grain.
if you have different grain from different that has been stored for different period. That could also be a blocking factor. So we need to first understand the difference between treatment and a blocking factor. What's the role of a blocking factor?
The role of a blocking
Yes.
factor is to determine how the different treatments will respond.
I think
Okay,
I think
another
the
person,
role of
Maria?
the factor is to limit the variance within the experimental unit.
Okay, to control
Yes.
variability. Okay, to control the variability. So remember here, let me go back to where we started from the other day. Remember here? So here we are comparing our treatment, which are the energy drinks, no?
Yes.
Yes. Okay? So here, what do we block in this case with? What is the blocking factor and what's the treatment?
The blocking factor is the different energy drinks.
Yes. Okay. So the treatment is what we want to compare. The blocking factor is what will confound our comparison. What will make our comparison difficult if we don't get rid of. So in this case, then when we go back. Both variety and moisture content as treatment, but it's also possible to use moisture content as a blocking factor. So in that case, the interest will only be to compare the variety. If I want to compare different varieties, let's say I have 5 different varieties that I want to compare. Now I can compare the 5 different varieties at low moisture content. I can compare them at mid moisture content. I can also compare them at say at high moisture content. So in that case, I'm using the moisture content as a blocking factor so that I can make my comparison well. Otherwise, then it will be a problem. So I need example now of 2 blocking factors for a Latin square.
Doctor,
So more examples? Yes.
for example, in watershed, we would consider the type of the soil and the vegetation cover if you're testing how water infiltrates in the soil. So the type of the soil and the vegetation cover would act as the blocking factors. Yes, doctor, are you getting me?
I think he has gone off a bit.
Again?
Yes, so and the blocking factor. For example, if I want to test the infiltration capacity of the soil, then I would consider the infiltration rate will be the treatment. Then
But then what are you measuring?
I'm measuring the infiltration in relation to soil type and vegetation cover.
Okay.
Yes, for example, in
So
a
what is
given
our treatment?
the treatment is the water that I'm applying. How will it move in the soil? For example, either on a rainy day or just physically applying it. Yes, therefore the two blocking factors would be the vegetation cover and then the soil type.
Doctor.
Can you guys give your opinion on his example? Yes. So there are 3 things here. There's infiltration rate, there's the soil type, and then there is vegetation. Okay. So we want to know which one's the treatment, which one is a blocking factor, and at the end of the day, what are we measuring? What are we measuring?
At the end of the day, we are measuring infiltration rate.
Infiltration rate. And what we measure, what do we call what we measure in an experiment? Because at the end of the day, we are going to compare the infiltration rate of the different soil type, right?
Yes.
So the infiltration rate is the outcome.
Yes.
Yes.
Okay. So it is not treatment; it is an outcome. It's what we call variable that we measure, no?
Yes.
And we want let's say we want the relationship between infiltration rate and soil type.
Yes.
Okay. So in that case, I can look at the infiltration rate of a sandy soil. I can look at infiltration rate of a clay soil. I can look at infiltration rate of, say, loam soil. This can be my 3 treatment. Now, if I want to bring in the issue of vegetation, then I said, okay, maybe I can use vegetation. I say, okay, can I compare the 3 types of soil when I'm in the forest, when I'm in a wetland, or when I'm in maybe a savanna? Okay. So in that case, therefore, I'm trying to compare the 3 types of soil, and I want to see, do they differ in relation to the filtration rate? And then if I want to control, I can then control for the different maybe environment from which the soil have been picked. Is that clear?
Yes, doctor.
So in that case, we say we have only one factor for control. I want 2 factors that we can use for control.
Doctor.
Yes.
I think I can, when I'm looking at studying the dietary requirements basing on age and then gender. So I think the dietary requirements could be the experiment, then the other two could be the blocking factors, because you find that at different age groups, for example, when you look at those like the younger ones will require a higher dietary input than the elderly.
So what are you comparing?
I'm comparing the dietary requirements for the different, first of all,
Yeah,
according to
but
age.
is the dietary requirement what you're going to change in your experiment or what you're going to measure?
It's what I'm going to measure.
So what you're going to measure is not a treatment. It's the outcome of the of applying the treatment. So what are the treatment here?
I
What
think
are you trying to? Whom are you trying to which group are you going to? Are you trying to compare?
I'll try to compare the young and the elderly group. Those ones maybe above 60,
Okay.
and then the young ones maybe below 45.
Okay. So you can see what you're trying to compare is what is your treatment. So if, for example, you want to compare age or groups like age, you said young children, maybe adults, and maybe youth, children, youth, middle age, and then old people. So those are the category that you want to compare. And what are you going to measure? You're going to measure the dietary requirement. Okay.
Yes.
And then if you want to control for something, then what can you use for control? Maybe you can control using different races. Do you think the same thing apply to maybe black people compared to white people, or compared to Indians compared to colored?
Yeah, I think so.
Okay. I think the more example we try to give, the probably the better we get in terms of understanding what we are talking about here. Another example? Albert, I need an example from you. Albert Nuwagira. Can you unmute yourself?
Yes, doctor, I'm here.
Yes. Yeah. So give us two factors that you can use for blocking an experiment.
Well, if you are say testing the sensory the the degree to which people are liking, say maybe your food product, you could change.
Okay.
You could change, for example, you could change some of the ingredients. For example, you could maybe change the salt concentration, no, the sugar concentration, and maybe also
Okay.
Yes, maybe the salt and then the acid that you are adding, the sugar and the acid, because they all affect how people are going to perceive the taste of the product.
So you're going to get some products.
Yeah, say maybe juice.
With different salt, sugar, and acid combinations.
Yes.
Okay. Is that what you're saying?
Yes, that's what I'm saying. Yes.
So let's say we have 5 of them. You're comparing them. What will you measure?
What I want to measure is the degree of liking. There is like a scale you can use, and say from 1 to 9, the degree of liking,
Okay, good.
which will reflect,
Yes.
which will reflect how people are liking the product. But then
Okay.
this perception is contributed to by the interaction between sugar and then also the acid, like the sugar acid ratio.
No, no, that will be part of the treatment. That will be part of your treatment, no?
Yes. Oh.
So you have the different acid, salt, sugar
Mm.
combinations. And then you want to see how people will, I mean, how people will rate that in terms of maybe how nice it is,
Yes,
yes?
yes.
So is the treatment clear? What's our treatment here?
The treatment are the sugar acid combinations.
Okay. And what is the variable that we are measuring here?
It's the test, the degree of likeness,
Okay.
the test of the product.
Okay, that is good. Okay, now can we then bring in the blocking factor?
Yeah, the blocking factor from what you said earlier on, you said it should, they are like characteristics of a population which help us to control variability.
Okay.
So maybe we could look at our population and say
Yes.
one factor, we have say the men, and then the other
Okay.
side we have the women.
Okay, yeah, that could be good blocking factor. Another example, good blocking factor.
Yeah. So that would be in terms of gender. Another one could
Yes,
be in
gender
terms
would be
of
one.
maybe another one could be in terms of
Could anybody can come in? Could be age, for example. You have young people, you have children, you have adult. Because they have, I mean, people grow older, they have different taste buds, no? So potentially, could those affect?
Yes, it could affect.
Yeah.
And then also would look at also some people, there are those that are vegetarians and there are those that are not vegetarians in terms of testing
Okay.
the sugar levels.
Yeah.
Then there are those people who are very sensitive. Like for example, the health bit of it, those that are maybe diabetic
Okay.
and those that are not.
Okay. I think the discussion is progressing quite well. So for a Latin square, for example, Maria will come to you. So for a Latin square, for example, we could use, let's say, for example, we could use, let's say we use tribe, for example. You say, okay, I have three different tribes. Maybe I have a Lugwara, I have an Itesos, and then maybe I have the Bajankoles. And those could be controlling factors because, well, they eat different things, so they may have. But then I can also use the age group in those one there. So I can have one factor which is based on the tribe, and then I have another factor which is based on the age. So you can have then, you still have your Logwara who are young, you have Logwara who are middle age, you have Logwara who are old. Then you have also for the other one. So that will constitute what we call a Latin square. Yes, Maria, your hand is up.
Yes, I wanted to give another example of
Yes, please.
perhaps the adoption of infant and young child practices. I
Yes.
can look at the income level of the population as well as the education level
Okay.
as the blocking factors.
So why
Yes.
would you want to, just to understand, why would an income be good for use as a blocking factor?
Because people of different income levels may respond differently, and therefore,
Yes.
the adoption of the new practices may be different because of their income level.
Okay.
Mm.
Yeah, that's good. Education status of the mother may actually be very important as a blocking factor.
Yes.
Yeah, if for example I'm comparing different feeding, I can block using different mothers because the mothers may apply the things differently, and that can affect the comparison that I will have.
Yes.
Okay. Any other person wants to? Yes, continue, Maria.
Doctor, I have a question.
Yes, please.
how do the blocks differ from like the clusters we discussed at the start of the course?
Yeah, the cluster idea of clustering is used in surveys. In experimental design, we look at blocking. There are similar ideas. Okay, it's all about grouping
Yes, yes.
experimental unit. Give grouping
Mm.
unit, the study unit, into where groups where there's similarity. But you see now, the idea of a block is more closer. Yes, idea of a block. A block is more similar to a cluster
Mm.
than to a stratum,
Yes.
because within a block there's supposed to be uniformity.
Uniformity.
Okay.
Yes, it's understood.
Yeah, experimental unit in a block should be uniform, and that's why we also say in a no, sorry, a block and a stratum is similar. Within a, remember, stratification also, we are grouping we are grouping our observation unit into groups within which there is homogeneity within the group and differences between the group. But for cluster, a cluster is supposed to contain everything that you're trying to study. So a cluster is not homogeneous. A cluster is supposed to be heterogeneous. But but a stratum is supposed to be homogeneous. So remember, we talk about stratified random sampling, and then we talk about cluster sampling. So with cluster sampling, we sample the different groups. We sample the stratum, and once the stratum is sampled, then you study everything within the stratum. While when you're doing sorry, I'm trying mixing up things. In cluster sampling, we sample the clusters and then we study everything within the cluster. In stratified sampling, we do simple random sampling within each cluster. So all the clusters, all the stratums, sorry, I'm mixing up the cluster and the stratum. All the strata, all the stratums will be studied. So let's say, for example, you divide up the country into the northern, the central, the eastern, the western, and then the southern part of the country. So with the stratified sampling, we are going to do random sampling in each of the region that we have. And we assume in this case that within the region, there's uniformity. And the region here represents a stratum, which is similar to a block. But with cluster sampling, on the other hand, once we divide this country into different clusters, then we randomly sample the clusters. So if, let's say, we sample two clusters, we sample the eastern and we sample the western, then we go to the western and study all the elements within the western. We go to eastern, we study all the elements within eastern. The cluster that have not been selected will not be studied. Okay, I don't know whether I made it clear or I made it more confusing.
I think it's clear.
Okay.
Doctor, I have a question.
Yes, please.
Is there a possibility of the two blocking factors to confound each other?
Yeah. Well, it's possible. So when you're trying to do the blocking, first of all, the classification or the grouping should be very, very clear. If the grouping is not very clear, then it may be difficult to generate groups that actually will make you a better comparison. Yeah.
For in the
So
previous slide,
let's. Uh,
in the previous slide, you're talking about where we had the slope against the fertility gradient. When we're
like here.
testing, like here now, the tree shading and
Okay.
fertility gradient.
Yes.
So maybe the shading is overshielding the expression of fertility gradient. How can that be explained?
No, no, no. That will not be a problem, because when you're finally coming to do the analysis, you're going to correct for both of them. Because remember here, if we look at the corner here, I don't know whether you're seeing the cursor. Have you seen
Yes,
the
doctor.
cursor? Yes. So you see where the cursor
Yes.
is. Now this would be low treat shading and then low fertility, because the plot here, this plot here will have low shading, and then will have low fertility, while the plot down here will have high shading and high fertility.
Yes.
So you have these combinations here. Let me first try to answer some call here.
Guys, just help me out here. Maybe you will help me understand what the lecturer is talking about with these blocking factors and variability. Supposing I had my two variabilities, I think, as tree trunk size and age, when I'm looking at quality of wood, what could be the blocking factors? What exactly are we talking about? I'm not understanding. Guys, just help me out.
Okay, sorry. Okay, so the whole idea here, are you getting me?
I'm getting you.
Yes, doctor, we
Yes.
get you.
Okay. Yeah, so the whole idea here is there is actually no confounding. The only challenge may be, remember here the assumption is that there is some kind of a perpendicular direction here. Now in the lab, for example, let's say for example you have 4 technicians that you use to run your experiment. Remember, each technician may be different, so you can use technician as a blocking factor, but you could also run your experiment in what we call different days of the week. So let's say you have Monday, Tuesday, Wednesday, Thursday. So you have 4 days in a week, you have four technicians. So you can use the day of the week and technicians as two blocking factors to help. Because remember, there may be differences in the day of the week. There may also be differences in how the technicians run their do their thing. So in that case, you need to control both factors together. Now, if in animal science, for example, if you are looking at the effect of, say, feed on milk production. Now remember, when the animal has just produced, the different period or what called lactation period may have different characteristics. So you could also block using the different lactation periods, and then you also block using, say, another criteria, like, say, maybe a milkman or whatever you want to have. Is the issue of blocking and Latin square clear?
Yes, doctor.
Okay. Okay. So here, for example, you can have a situation where you have machines. So I have treatment A, B, C, and D that I'm testing in the lab, for example. But I can run, let's say I can run, I have four incubator 1, incubator 2, incubator 3, incubator 4. And then I have four different technicians, say Mr. Okelo, Mr. Mukasa, maybe Mr. Okirol, and then say somebody called James. So what we can do is then that we can run treatment A, treatment C, treatment B, treatment D in machine 1 at different time using different technician. So you can see that technician operator 1 run treatment machine 1 for treatment A. It also runs with treatment B, B for treatment machine 2, C machine 3, and D machine 4. So you can see that in a Latin square, if we are using this as a blocking factor, you can see that operator is a block. Operator 1 is a block, and you can see there's all the treatments are in operator 1. So this is a complete block. Operator 2 is also a complete block. Operator 3 is also a complete block. Operator 4 is also a complete block. So if I only look at operator 1, 2, 3, and 4 as a blocking factor, I can see that I'm running a randomized complete block design with each operator as my blocking factor. But I can also look at the same experiment from the machine perspective. So remember, machine 1 will have all the treatment. Machine 2 will also have all the treatment. Machine 3 will have all the treatment. Machine 4 will also have all the treatment. So I have two blocking factors here. I have operator as a blocking factor, I have machine as a blocking factor, and then I combine the two will give me what we call a Latin square design. Is that clear?
Yes, doctor.
Okay, so here is another example. So here, for example, I have week 1 of the study, week 2 of the study, week 3 of the study, and week 4 of the study. Remember, if an animal has just produced, they will have different characteristics in the different weeks that I want to study. So we can use the week as blocking factor. Week 1, week 3 is different from that animal, is different from that animal, is different from that animal. So remember here, what we are comparing here is we are comparing the different drugs here. We have the control, we have low dose, we have medium dose, and we have high dose. So these are what we are trying to compare, but we want to control for the time when you compare the treatment, and then for the different types of the animal that you actually use in your experiment. Okay. Is that clear?
Yes, it's clear.
Design. So the row column design in this case is then, if we go back here, uh, this is row number 1, row number 2, row number 3, and row number column. This is what we call a row column design. in row 1, the control is here occurring only once. In row 2, the control is also here occurring once. In row 3, the control is here. In row 4, the control is there. And then low dose is here, low dose is here, low dose is there. And then you have low dose there. So if you look at the row alone, this is row number 1, you have a complete a randomized complete block. You go to row number 2, you have a complete block. You go to row number 3, you have a complete block. You go to row number 4, you have a complete block. And then if you look at the week also, column 1, you have a complete block because all the treatments are there. Column 2, you also have a complete block. Column 3, you have a complete block. And column 4, you have a complete block. Okay? Okay, so here the number of replication is actually equals number of rows and equals number of column and also equals number of treatment. So what this one means is that if you have 5 treatments, that means each treatment needs to be replicated also 5 times. And in that case, you need to have 5 rows and 5 columns. So if I have 10 treatment, then each treatment also has to be replicated 10 times, 5 times. Now, let's assume I have 10 treatments. How many experimental units do I need for my experiment? Because if I have 10 treatments, each one needs to be replicated 10 times.
Yes.
So you need 100 experimental units. So that means if you're using test tubes in the lab, for example, then you need 100 test tubes because each combination of the 10. Okay?
Yes.
So the total number of experimental unit is the square of the number of treatment. So if I have 5 treatments, the number of experimental unit that I require will be 25. If I have 10, the number will be 100, and so on and so forth. So you can block using 2 factors, what we call row and column, and then we expect that in this case, the experimental error will be a lot more controlled compared to if you only block using 1 factor.
Doctor.
Yes.
So in Latin square, we expected we expect the variance to be very low because of high control.
That is an ideal case. We expect it to be low. Yes, because you are now trying to control the variance in 2 directions. But we are going to see at some point that when you're doing the blocking, you actually making some sacrifices. So for you to get low variance, you need to ensure that your blocking is good. But if your blocking is not good, then you may actually not benefit very much from the blocking. And that's why you say we need to understand our experimental material very well so that we design an efficient blocking.
All right.
Okay?
It's okay.
So the limitation, one of the limitations of a Latin square is that because of the square requirement, like say if you have 10 treatment, then you need to have 100 experimental units. So in a way, then it can make the experiment very, very large. So if you have very many treatments, then it becomes difficult for you to use a Latin square design because it will require you to have a bigger set of experimental units to use. And then the other reason why Latin square may be a problem is that if you have an experiment with very few treatments, let's say you have only 3 treatments, then you're going to have very few degrees of freedom when you're constructing your analysis of variance, and few degrees of freedom when you're dealing with analysis of variance means that the experiment is inefficient. You will not be able to detect the differences that exist in your trial. So your experiment, in a way, might have very low power. And then there are several incomplete Latin square that are there that you can use. The most famous are what we call the Jordan squares, so Jordan design. So these are used in case where the Latin square cannot be used because of the size issue. If the experiment becomes very big, then you may have some kind of incomplete Latin square design. Okay.
Doctor,
Yes.
how few or how small is it considered to be small, and how large is the experiment considered to be large?
For three of if any experiment with three or four treatment will be considered to be small, and then for large anything from 10 experiment upward, 10 treatment upwards will be considered to be large, but that is large in relation to the field experiment. If you're doing an experiment in the lab, for example, if you're dealing with test tubes, if you have 12 treatment that you need 144 units, so it could still be very big. So anything from 10 upward can be considered a large experiment.
Then anything below 5, it's small. Or 4.
Below 5 is small.
Okay.
So it's 3 and 4. 3 and 4 literally, you cannot have 2. 2 will almost not be an experiment that you would conduct. So 3, you have very few degrees of freedom. 3
All
and
right.
4. Okay.
Yes.
So we can also use ARA to generate the design. So in a way, you what you can actually do, you can even copy these commands here and use it to run on your ARA. I'm going to open ARA at some point, and then we go, and then we can have that. And then the other experiment is what we call a split plot. So a split plot is used when you have what we call a factorial treatment structure. So a factorial treatment structure is when in an experiment you're testing more than one treatment factor. So if, for example, let's say you're testing the effect of time and then temperature. So let's say you're testing the effect of time on the quality of bread. So I can, for example, compare let's say three different times. I can say maybe baking for 45 minutes, baking for 60 minutes, and baking say for 75 minutes. So this is in this case I have a factor which is time. And then maybe I also want to say, well, what if I bake at different temperatures? Maybe at 110 degrees centigrade, 120 degrees centigrade, and then 130 degrees centigrade. So I have two factors I'm trying to test here. I have temperature with 3 levels, and then I have the other one is time also with 3 levels. So in that case, I have two factors that I'm testing. That's what we call a factorial experiment. We are going to look at it probably at some point in time if we have time. Okay. So in this case, one factor may require a larger area for application, so it's mainly used for logistic. So let's say, for example, we are looking at the issue of temperature and time. Now, if I'm going to use, if I'm going to, let's say I have 3 different temperature as I indicated, I have 110, 120, 130. And then I have time. I have time which is like, I said 45 minutes, I have 60 minutes, and I have 75 minutes. Now, if let's say I'm going to use an oven for as my experimental unit, how can I design an experiment that will add both factors together. I mean, I want to your opinion. Now, what can I do? I mean, I have one oven. What can I do in the one oven? Can I make it uniform time? Can I make uniform temperature? Oh, this becomes very complicated. Can I
Doc-
combine these two together? Of course, what I could have is I could have, I wanted to write a pen. I don't see a pen here. Oh, let me check whether I can have a pen.
Doctor,
Yes.
I think we can combine the two factors.
Hey, how?
For example, in that very oven, you can test the two factors at a given temperature at once with all the other factors. For example, if
So
it's 30
I
minutes,
can have an oven. I can
you
have
split
oven which is set at
at 30 degrees.
uh,
After that,
with the okay 30 degrees, maybe 30 degrees for 1 hour.
for 1 hour. Then
Then I have
after,
another one.
and then you still use the same and increase the temperature and the time. Yeah, you do one step at a time. Since it's one oven,
Okay.
yes.
Now what if now let me see. Okay. So here one factor will require a larger area for application. So a Latin square can be used with the completely randomized design, can be used with randomized complete block design, and can be used with a Latin square design. So it is more of kind of we arrange treatment, a treatment arrangement rather than the design itself. So what it does is, I'm going to illustrate using the next slide. So what it does, it involves splitting a larger experimental unit into which the first factor is applied into smaller unit onto which the second factor is applied. So let's say, for example, here we have a tray. This is a tray of seedlings. Okay, so we have tray A and tray B. Now, if let's say I have different varieties, and then I also have fertilizer. Each I can plant, like line one, I can plant one variety. Line two, I can plant another variety, and so on and so forth. Now, will it be easy for me to apply fertilizer, different fertilizer in the different lines? Let's say I'm using a liquid foliar, I mean fertilizer that I apply directly on the, I spray the leaves. Will it be easy for me to use, to apply, let's say I have line one, it has variety, maybe variety J, and then I also want to apply some kind of, I want to apply some kind of a fertilizer on the leaves. Will it be easy to do that without contaminating the next line?
Yeah, I don't think it's easy.
No,
It's hard to.
it's not easy.
I think
Okay.
the
Yeah,
best
go ahead.
the best option would be giving all the lines the same fertilizer, then maybe you vary other factors. But if you want, since they're on the same tray, it's a little bit hard.
It would be easier to actually apply fertilizer over the larger area, and then the line you can apply, you can use different varieties, which is okay, because I know I can easily plant this without actually contaminating the next one. So this is where split protein becomes important, is mainly when you have challenges on how to apply your treatment. So here we can apply a treatment that require larger area on the tray as an experimental unit, and then a line here as another a subset of this now. So this becomes what we call the main plot factor or all plot factor. It will have a particular fertilizer. And then you divide this into sub. So each of these line now is sub plot within the bigger plot. So this is what we call a split. So the bigger one gets split into the smaller one. So you can have a room, for example, that you set at say 110 degrees, and then within the room you can then have you can compare different chemicals in the room. But because it will be difficult for you to partition the room and apply different temperatures in the different compartment within the room, so it will be easier for you to get one room, or you get one oven and apply a uniform. I mean, you cannot divide an oven into two and apply different temperatures. So the best thing would do, I can get one oven. I'd say this oven is going to be at 110 degrees. Then I can compare the different ingredients for making bread inside that particular oven. So the oven itself is a bigger experimental unit to which we apply temperature as our factor, and then within that we subdivide by putting the different ingredients of the different content within that. Okay, that would be what we have here. So that is what the splitting is. A question? Anybody with a question? Split plot is used with factorial treatment structure. One factor require a larger area for application, so mainly used for logistic reason, like we demonstrated here, that this one, the spraying with fertilizer would need a bigger area. So one factor require a larger area of application. So it can be used with either CRD, RCBD, or Latin square. And it is more of a treatment arrangement than the design itself. So here it involves splitting a larger experimental unit onto which the first factor is applied into smaller. So here, for example, we can have our block here, split it into two. We have no spraying versus spraying. So I could look at this. This could be spraying and this could be no spraying. And then we can then plan the different varieties as the subplot within the bigger plot. So then line here, maybe the first two line will be our variety 1, variety 2, variety 3, variety 4, variety 5, variety 6. Okay? And we have to break this one up into the different components that we have there. So the splitting here can proceed as long as it is required. And then randomization for the different levels of the factors are done differently. So here I can do randomization for the big plots, and then within the big plot I do another randomization for the small plot. Okay? So the implication is therefore means that when I'm going to analyze my split plot design, I have two experimental errors. Remember, experimental error is related to the randomization process. I have experimental error for the main plot, and then I have experimental error for the subplot. So there are two different experimental units, experimental error that you can actually use for testing the different factors. So this is how it will be generated. We're going to look at this. Okay, so that is our design. Any question?
Doctor?
Yes.
How do you know that my experiment needs, I'm going to use split design?
Yeah, but that's what we have been talking about, that if the first question is, I mean, first thing is that clear?
Okay.
The second one, therefore, is that one of the factors may require a bigger area of application or logistically it may be easier to handle one of a larger unit compared to the other. So that's the second reason. So the first one, it has to be a factorial experiment, and then the treatment that you're comparing or the factors that you're comparing should have different requirements as far as application is concerned. And those of a wider area compared to the one that will be over a smaller area. So that will determine how you can do that. But it could also be in terms of the logistics, the availability of resources itself. So if I have fewer rooms to do an experiment, I would resort to a split plot because it enables me to put several subplot within the bigger plots. Okay. Any other question?
Doctor,
Yes.
is there an experiment where there's a combination of the completely randomized design and then the block designs?
No. I mean, you can add either completely randomized design and then you have randomized complete block design. The split plot can be applied to any of those. So you can have split plot with CRD, you can have split plot with the RCBD, but you cannot combine RCBD and CRD. The main assumption here is that with the CRD, the experimental units are uniform or homogeneous. And with RCBD, the experimental units are not homogeneous. That clear?
Yes, it's clear.
Any other question?
Doctor.
Yes.
Yes, now may I just have this, if we use, let me say, the split of design and maybe the CRB, that increase its precision, it's more like zero.
The split plot is the split plot advantage of a split plot is mainly relating to how the treatment can be, how easy it is to actually arrange that, how easy it is to manage the experiment. But in terms of statistical efficiency, it is not the most efficient design. You rather use your RCBD or use your CRD rather than using a split plot. A split plot, you have to be conditioned to use it by the challenges that are related to the logistic of your experimentation.
Okay.
Yeah. Any other question?
Yeah, I'd like to clarify the example that was given of the oven. So what if within this oven you have a particular temperature that you're trying to assess, and then you put in different maybe units of bread for the different time. For example, it's at 60 degrees, then you take out one loaf after 30 minutes, another loaf after 60 minutes, another loaf after maybe 1 hour and 30 minutes. So would that be having a split plot in a way? Because
It may not have a split plot in a way.
Then you do it again for
The
another
challenge
temperature.
for a split plot. Okay, yeah. I mean, the oven at 60 is what you can do is that an oven can take more than one bread, no?
Yes.
Yeah. So if I set an oven at 60,
yes,
I can then put my different ingredient in that. That will be a split plot.
Okay. So
yeah, but if I say I put one, I remove, then I put another and I remove, then you're going to also get challenged with the issue of the blocking again. Because when I'm putting one, you see, if the first 30 minutes that I run an oven, and then I bring another one, I put another 30 minutes, that's going to be different now. It's going to bring you another challenge.
No, what I'm saying is if you want to, we are trying to look at the time, we have the time as a factor as well as the temperature. So we have the one oven, we keep at a particular temperature, but we put in all the breads at the same time, but we remove one, all of them are put in at the same time. But the first loaf is removed after 30 minutes, the other, but the temperature is the same. So you have the first removed after 30, the next one after 1 hour, the next one after 1 hour and 30 minutes. Then you change to you get
Well,
two different
that would do. Yeah, that would do. That, yeah, that could be considered to be a split plot. The only challenge may then be in the process of removing and taking back, removing and taking back, whether you will not include, you will not bring in some other
Yeah.
issues.
Okay.
If you
All
can
right.
do it perfectly, that would be fine. Yeah.
All right. Okay. Thank you.
Okay. So the selection also depends on how easy or difficult it is to do what you're talking about. So before I mean, when you're trying to make a decision on which design to use, these are the things you need to sit down and look at because they will help you to actually move through, design your study suitable. Otherwise, then you will be in problem if you don't look at that.
All right. Thank
Okay.
you. Yes.
Okay. So I'm going to give you tomorrow. We are going to have to start our. We're going to have an introduction to ARA, so that we are able to do the other analysis in ARA. Now I'm going to ask you to go and watch. Go pick YouTube. Go to YouTube and pick any. Pick any introduction to R video and watch. But let me try to see whether I can get a link to one of the videos that we had for the training and share with you and ask you to go through that, so that by tomorrow, when I come in, it will be a lot more clearer. I'm going to look at a video and give it to you. Tomorrow, I want everybody tomorrow to have R and R Studio installed on their computer. And I'm going to request each one of you to share the screen to prove to me whether you have it or not. Okay? So there is no way you're going to lie to me. So between now and tomorrow, please put in, get your, or else if you don't, I want to show that your two of you are on the same, you show me your faces on the same computer, then you can work as a two or three. But I need that proof tomorrow. Okay? So we can end for today here, so that I give you time to go and finish up to and have your Valentine celebration.
Doctor.
I don't want to be the cause of your marriage breakages or your relationship breakages.
Doctor.
Yes.
Doctor.
Yes.
Are we meeting tomorrow the same time and online?
Yes.
All right, sir.
Thank you, doctor.
Thank you so much.
Lining up.